Okay, so we're still doing this kind of recap of stuff for um, the electronics part of the course, because that's going to be our first assessment. Today's recap lesson is going to be about logic. Okay, first things first, you need to know the three logic functions that we use in National 5. Not, sometimes called an inverter, and or. So the idea here is that if you use the not function, whatever you put out will be inverted. Sorry, whatever you put into that function will be inverted. In an and function, we would say that the output would be on if input A and input B were on. Basically, all of the inputs have to be on for the output to be on. And then or, the output will be on if any of the inputs are on, A or B. You need to know the symbols for these gates. You need to be able to draw them. That's the symbol for a NOT gate. I'm just going to label the input A and the output Z. Obviously, in the systems that we talk about, the names of the signals might be predetermined. Like, you know, if this was a light sensor, it would be L/S as the input. And then if it was a light sensor that was feeding a signal to an alarm system, that might be A or AS or something. Right, okay, the AND gate, the symbol for the AND gate. So basically you're drawing a big capital D with an output and a minimum of 2 inputs for the AND gate. In National 5, we'll only ever use gates that have 2 inputs. Again, I'm using these arbitrary names. And then for the OR gate, you use 3 curvy lines. And again, same as the AND gate, a minimum of 2. In National 5, we'll only ever use 2 input gates. So that's the names of the logic functions and their associated symbol. You need to be able to write the Boolean term for these. You need to be able to write it down. It's helpful to be able to say it as well. So if I was describing this, how would I vocalise this? I would say that Z equals not A, and I would write it like that. So that is read out as Z equals not A. Over here, I would write Z equals A and B. So that would be A and B. Big black dot right in between the 2 letters. Z equals A and B. These are the Boolean terms. And then this one's A or B. Z equals A or B. And I know it's a plus sign and everybody complains, but that's just the way it goes. So just to clarify, I just want to kind of this is the function. This is the symbol. This is the Boolean term. And then we've got a truth table. Okay. So for the truth table, a truth table is where we map out all the possible combinations of input and show what the outputs are for them. So in this case, we've only got 1 input and 1 output. The input can either be on or off, and we show this using zeros and ones, where 0 is off and 1 is on. And then we map out what the output will be for that in a NOT gate. So if we put an off signal in here, if we turn A off, the output of the inverter will be on, because that's what an inverter does, it inverts the signal. If you put a 0 in, you get a 1 out. If you put an off signal in, you get an on signal out, and then vice versa. If you put an on signal on the input, you'll get an off signal on the output. So that's the truth table for a NOT gate. It's really important that we remember these relationships. Kind of easy to do for an inverter, but a little bit more thought required. Just a little bit more thought required for the other two. Now, this is where we talk a little bit about the kind of theory of these types of systems. These types of systems are called digital systems. Okay. Now, what that means is they use signals that are considered to be either on or off, right? Binary systems or binary signals. digital signals or binary signals are drawn or represented like that, where the signal is either at a low level or a high level, and it doesn't spend any time in between. This is as opposed to the opposite type of systems, which are analog systems. So in an analog system, any signal that exists in an analog system could be a low level or a high level, or it could be at any point in between. Yeah. Sometimes the wee kind of symbol that we use for an analog system is like maybe something like that. It shows it can go from a minimum to a maximum value or occupy any signal in between. But these systems are digital. It's either off or on, and that's it. There's only two possible states. Okay, that's why we can use 0 and 1 to represent the signals. When we're laying out a truth table like this, we don't want to accidentally miss any of the possible combinations, right? So there's a rule about how you lay out this side of the table, because this side of the table is always going to be the same if you've only got 2 inputs. And if you've got 3 inputs, it's always going to be the same. If you've got 4 inputs, it's always going to be the same. You just need to learn how to lay it out. It's easy enough over here. There only are 2 possible combinations. How many possible combinations are there when you've got 2 inputs? Or 3 inputs, or 4 inputs, or 5 inputs? You need to know so that you don't accidentally miss any out. So we've got an algorithm for laying out the input side of a truth table. So the first thing you do, right, so let's say for layout of a truth table. Step 1, work out how many rows there will be. Work out number of rows. You do this by raising 2 to the power of however many inputs you've got. Okay? So for an inverter system where you've only got 1 input, how many rows has a truth table got? 2 to the power of 1. That equals 2. For the system that we're looking at just now, where we've got 2 inputs, that means our truth table is going to have 2 raised to the power of 2, which equals 2 times 2, which equals 4. There will be 4 rows when you're using a system that has 2 inputs. So actually work out the number of rows. Step 2, fill out the rightmost input column. Alternates in singles. What do I mean by that? So what I mean is, if you've got let's say we've got A, B as an example. Let's see, we've got A, B and C as our inputs. How many rows is that going to have? 2 to the power 3. 2 times 2 times 2 equals 8. It's going to be 8 rows. So there's 1, 2, 3, 4, 5, 6, 7, 8. Right. Fill out the rightmost input column, alternates and singles. Alternates every line. Start with 0. Always start with 0. So off, on, off, on, off, on, off, on. That's how we alternate in singles. So you can see a single 0 and then a single 1 and then a single 0. Part 3. Fill out the next left input column. Alternate in pairs. So this would be 0, 0, 1, 1, 0, 0, 1, 1. I've moved to the next input column. I've went left by 1. I'm filling it in, starting with 0, but I'm making them appear in pairs. And 4. Fill in the next left input column. alternate in 4s this time. 1, 2, 3, 4. 1, 2, 3, 4. That's it. So then this would be continue until input table is complete, is filled. So you start from 0, you alternate every line, you alternate every second line, you alternate every 4. If there was a 4th input, then you can see it's singles in the first one, pairs, 4s, 8s in the next one, 16s in the next one, 32s in the next one. It's a binary system. It's based on a number 2. It doubles every single time. So you can see here that for a 3-input system, there are 8 possible combinations of input, and I've managed to identify all 8 of them. And I haven't missed any out, and I haven't accidentally duplicated any. So as long as you follow this kind of algorithm for creating the input side of the table, you'll never miss any out. You'll never get any wrong. The vast majority of times in SQA papers, you're given this, to be fair. But it's important that you know where it comes from, you know what it is, you know why it looks that way, and that you should be capable of doing it yourself. So when we look at these truth tables for an AND gate, we need to make sure the input side is correct. So 2 to the power 2, there's going to be 4 rows, 0, 1, 0, 1. And then this will be done in pairs, 0, 0, 1, 1. So you can see I've got all possible combinations, both off, both on, B on, A on. And that truth table, that kind of start for that truth table, is going to look exactly the same for the OR gate as well. Yeah, the input side's always the same. All we're doing is identifying all the possible combinations of input. So if you've got 2 inputs, it's always going to look exactly the same. It's the output column that will be different, because the output column is dependent on the function. So in this case, it's A and B. So an AND gate, the output column will be on. The Z will have a 1 in it, wherever both A and B are both 1. So A and B are both 1. There's our 1 there. Oh, there's our 1 there. And the rest will be 0, 0, 0. For the OR gate, the output column will be on. The Z will be on if either A or B is on. So B is on here, so there's going to be an on signal. A is on here, there's going to be an on signal. It's irrelevant that they're both on. You can still make the argument, the logical argument, that one of them is on, and therefore the output is on. And that's our 3 truth tables for our national 5 gates. So a NOT gate looks like that. Z equals A, Z equals not A. That's the Boolean term, how you write it. That's what the truth table looks like. And then the same for the AND gate, and the same for the OR gate. Z equals A and B. Z equals A or B. That's the basis. That's the basic information for logic. What are you asked to do with this information? You're asked to design logic circuits. You're asked to write down Boolean terms. You're asked to complete and create truth tables. So let's do a couple of examples. Let's say you're given a logic circuit that looks like this. So this is like a combinational logic circuit. You might be asked to P, Q, R. You might be asked to identify what the Boolean term for this circuit is. What does Z equal? It can be really, really helpful to name certain things, to make things just a little bit simpler. Like for instance, you can see this black line here represents the input P, and this one represents the input Q, and this one represents the input R, and this one represents the output Z. What does this line represent? It doesn't represent P because it's on the other side of a NOT gate. That's not an input and it's not an output. Same as this line in here. That is neither an input nor an output, and call them intermediate signals. What you should do is label these intermediate signals. PQR, I'm going to call that one A, and I'm going to call that one B. These are intermediate signals, they're not inputs, and they're not outputs. And then you should write down the Boolean expression for them. A equals not P. A is the output of a NOT gate, where P is the input to that NOT gate. So A equals not P. And B equals A and Q. A and Q. Because this is a combinational logic circuit and there's more than one gate, I'm going to put brackets around anything that is a gate on its own. Alright. Z equals, I can then do the Boolean term for Z, but I can keep it dead simple. Z equals B or R. Yeah. Now, R's an input, but B isn't. B is an intermediate. I need to state Z only in terms of inputs. So I need to substitute in what I know B equals. So wherever I see B, I'm going to put brackets A and Q. So it's A and Q or R. Notice the brackets. A is an intermediate signal, it's not an input signal. So I'm going to have to substitute in what I know A equals, which is not P and Q or R. And that's the Boolean term for Z. Okay. Some people might be able to see it just by looking at the circuit, that it's not P and Q or R. In this case, it's a bit more simple to do that, and some circuits can be a little bit more complex. And this identifying the intermediate circuits, so identify those intermediates. And you can identify them by the fact that they go from gate to gate. Yeah. Write out the Boolean for the intermediates. That's what I did in purple. Write out the Boolean for the output. That's my first red line. And then substitute the intermediates into the final one. That's how you get a Boolean term from a circuit. And vice versa, if you had a Boolean term, you should be able to draw a circuit from that. Okay. The next part of it is, how do you do a truth table? So for instance, they could give you a circuit that looks like that. Let's go A, B, C, and there's Z. And they could ask you to do a truth table for that. So we're still going to have to use those intermediates. There's an intermediate signal here, there's an intermediate signal here, and there's an intermediate signal here. So it's 3 intermediate signals. We're still going to want to pay attention to them. A, B, C, I'm going to call that one D, I'm going to call that one E, I'm going to call that one F. I'm going to write down what they are. D equals A or C. E equals B and C. And F equals not D. Excellent. And I can say that Z equals, this isn't an intermediate, probably shouldn't be purple, F and E. Now you should be able to go ahead and get the Boolean expression for Z here. I'm not going to do it, you can do that. You can pause the video and do that now, I suppose. This isn't the actual question I'm doing, but yeah, you should end up with, pause the video now, because I'm going to try to write out the answer. Do it on your own before I do it. So that would be A or C, all not ANDed with C and B. With the brackets in that position. So that's what you should end up with a Boolean expression. But what I want to do is I want to focus on the truth table at this point. Okay, so truth table, we've got 3 inputs, A, B and C. So we would do our input side, so it's going to be 8 rows, 2 to the power 3 is 8, 0, 1, 0, 1, 0, 1, 0, 1. Then this one alternates in pairs. This is all the possible combinations of input. And this one alternates every 4 lines. I'm then going to include my intermediate signals, D, E and F. And then I'm going to put my output column in. So I should be able to complete this because I've got the Boolean terms. So D should be A or C. A or C. So if you think back to the truth table for the OR gate, you get a 1 when any of the inputs is on. In this case I'm looking at A and C. If I were to put 0, 0 into an OR gate, what would I get? I'd get a 0. If I were to put 0, 1, I would get a 1, 0, 0. I'd get a 0, 0, 1. I'd get a 1. It's important that you make sure you keep looking at the correct columns. It's A or C. And notice A is a 1 for the rest of them. So it's going to be on in the rest of them. So here's my D column there. F is really easy. F is not D. So whatever D is, F isn't. 1, 0, 1, 0, 0, 0, 0, 0. Then the E column is B and C. So if I put that into an AND gate, what would I get? I'd get 0. If I put that into an AND gate, I'd get 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, 1. Then my final column is Z, is F and E. So if I put that into an AND gate, I'd get off, 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 off. This system is never on. That's what I get for just making something up off the top of my head. Z will never be on. It's interesting because it's an AND function. Right, anyway. That's how we get a truth table from a circuit. You still have to do this intermediate bit, right? So we've got this one over here. When you go ahead and do the truth table for this circuit here. Okay? Again, pause the video, I'll do it and then you'll be able to see the answer. So pause it now because I'm going to start. So that would be 2 to the power 3 again, so it's 8, 0, 1, 0, 1, 0, 1, 0, 1. As I've said, most of the time you'll get this bit given to you, but you know, just in case. We've got our intermediates A and B, and then we've got Z as our output. Okay, so A is not P, so that's going to be 1, 1, 1, 1, 0, 0, 0, 0. B is A or Q, so I'll put that 0, 1 into an AND gate, A and Q, yeah. I'd get off, A and Q, off, on. Then the rest of them will be off, because A is off and the rest of them. And then Z is B or R. First one's off, 1, 0, it's on and on, because that's there. And then we'll go off, and then we'll go on, off, on. So that's it. That's everything that you need to know for logic. Okay. Now go ahead and do the past paper questions on logic. Thank you.